Great, thank you very much. So, yeah, my name is Martin Fergie, and I'm part of a startup based in Manchester called Digital Bridge. We sort of based in the home decoration space, so our kind of aim is to build really easy to use consumer applications that allow you to start experimenting with home furnishings. So, without too much ado, we'll jump straight to a demonstration. Unfortunately, it's really easy to communicate what we do. So, this is our kind of web app, so we built this as a sort of test to demonstrate to retailers. So what I can do is I can grab a picture from my computer. So we'll go for this one. And so what we do is we upload this to our application, and what happens now is we've got sort of the big bank of servers sat on AWS, which start to analyse the image and try and work out two primary things. It's sort of the geometry of the room, so where the camera is in the room and how it's orientated for everything, and also where the objects are. So what we can see is we've managed to work out the overall geometry of the room. So we've fit this box, which is actually constrained so that it matches the shape of the room itself. We've actually got this to fit itself automatically tonight, but due to one little bug, I didn't want to demo it this evening. So once to do that, it goes away, does a little bit more processing, and then within sort of, well, we aim for 10 seconds, sometimes it takes a little bit longer, we can start to decorate. So what we'll do, since we're in Manchester, well, based in Manchester, we can put some salford art. We can pop that on the wall. You see we've got the right kind of perspective to meet the wall. We also model the lighting, so if you pop it up here, it'll be quite a bit darker. If you move it down here, it gets lighter where it's lighter. We can then bob that onto the floor if we want, or up over here onto the wall. We can grab some wallpaper as well, so nice striky stuff. Stick that on the wall up there like that. And that fills in. Again, we managed to find where the wall is. Stick that over here as well. Completeness. And we'll do some flooring. Like that, and then we can also work with kind of 3D furniture as well. So let's grab this funny sideboard. So we pop that in there, and then we can move that around so you can move that in and out. And so what we've done is managed to automatically work out what the correct perspective is from the photograph, so we can start rendering virtual items in over the photograph as if they were there already. Our business is based around sort of accessing into existing retailer channels. So what we want to do is provide this application embedded into retailers' websites so that as a consumer you can have a seamless journey. So you might go onto your favourite wallpaper website and you browse through all the different samples you're interested in. Rather than having to order that and have it sent to your house and holding it up against the wall, you can then go, right, I want to try this in my own room, upload your picture, you're taken into our tool, embedded into their existing e-commerce journey, and then you can start experimenting from there. All our software works purely in the browser, so we initially started out doing mobile apps, so you'd have to download an app and then you'd be able to take a picture on the app and decorate it. We quickly learned that retailers didn't like that because that meant you had to go from the retailer's website, when you got the product, you then have to go via an app. That process loses customers, so we went through quite a big process of re-engineering everything so that it would work directly in the browser. While there's quite a few companies that look in this visualization space, ours is really focused around simplicity for the user. So within, say, 10 to 15 seconds, we want people to be experimenting with things, trying it out in their room. That's always the kind of guideline that we aim for. Cool. So what I'm going to do is I'm just going to talk a bit about Digital Bridge, about the company, and then I'll talk a bit about how we use machine learning in our platform. Wasn't quite sure how to pitch it for today, so I've gone for more of these are the problems we face, and a little bit of an explanation of how we go about tackling them without getting kind of too technical. And then I'll talk a bit more about what our future product roadmap is past this photo tool and the kind of areas we're interested in getting into. So, our goal, as I said earlier on, is to make it really easy for consumers to visualize home decorations. So there's a huge market of online sales for home decorations, which is somewhat untapped because people are scared to try and buy these things online because you can't try it out before you buy. So what we want to do is to break down that process and make it a lot easier for people to do this through building very easy to use applications. In order to make things easy to use, that's where we start to rely on sort of computer vision and machine learning in order to automatically understand the content of images, to stop people having to go through, a lot of the existing solutions. You're sort of talking about an afternoon. You have to sit there, draw out your room, put all the windows in, measure it out, and then it's much more engaged, whereas we're going for sort of mass consumer market, as it were. So this is us. You can take a few out and add a few more people now as times change. So there's about 14 of us in total, and we're kind of sort of about a third of us are focused on doing kind of research type tasks. So we look at kind of using computer vision algorithms, machine learning techniques in order to solve the various problems we come across, and I'll talk a bit more about those. We then also have a kind of a front end web team and a kind of computer graphics team. So we actually have a graphics engine written in C++, which we cross-compile to run in the web, and then we build a SDK around that, which allows us to then be embedded into other people's applications should they need. We kind of go for a very light touch on the user experience front, so people can customize it to suit what they want to do with it. So it's more of a platform as opposed to an application in a way. And then we've got sort of a product team and operations team, so they are in charge of, so one's product development, they go out and represent the user for us, try and work out what problems people face in the home decoration kind of scope. And then our CEO as well manages all the sales. So we've had quite a successful last couple of years in sort of the publicity sense, and so this summer we run the John Lewis Accelerator program. So this was an 8-week program in London where we were embedded in John Lewis offices and were able to access their product teams and all their kind of e-commerce teams. Really interesting experience for us, and we were very fortunate that we won the Partners Award. So all the John Lewis partners voted for our product as the winner of this year's program. That got us lots of good coverage in the Times, which has been very useful. We also won Retail Week Live, started the year last year. So this is a big retail event where all retail executives from all over the country, and actually some international companies as well, come, and it's about promoting different retail products there. And so they voted us as the kind of the best product of that year. Well, it was a joint one with a couple of other ones as well. So yeah, things are going well. We're based in Manchester Science Park, so just near the university, which is a very good location for us. Because lots of students come out of university and we're there ready to catch them. So next I'm going to talk a bit about what problems we face, like what the main kind of machine learning related problems that we have to tackle in order to build an application like this. Just to give you an intuition. So the two primary problems is, so earlier on we're looking at first getting the structure of the 3D room. So, and I'll talk about a bit more of this in a minute, but when you take a picture with a camera, you're taking a 3D world, projecting it onto a two-dimensional plane, and you need to understand the process that goes into that, which basically allows us to kind of draw a virtual transparent room over the photograph, which matches its geometry, so we can start to then add in virtual items on top. We combine that then with what's called image segmentation. So here we're trying to say, okay, we want to know which bits of the image are wall. So if you click on a wall, we want to find that entire wall, but we don't want it to run onto the floor or onto the ceiling. That's actually a very complicated problem. We spend a terrible amount of time trying to do that. So what we'll start is just talking a bit about how we go about this 3D geometry problem, what the issues are and how we solve that. So, I don't know, I've gone for this kind of using ArtView because everyone's quite familiar with perspective when used in art, because you've all probably done it in art class where you draw the point in the distance and then all your buildings disappear off so you can get perspective. So, as I said earlier on, so when you take a photograph of something, you're taking a three-dimensional world and projecting it onto an image plane. And that's what the illustration on the left shows. So we have the gentleman on the left is taking the point in the real world, and is getting projected through an image plane. In this case, it's a frame, up to a fixed point on the wall. And then as you sample these points, you start to make an image of what the 3D object is projected through that plane. Now, again, and the effect of this is that if you look on the right-hand side, is that parallel lines in the real world will collapse down to a vanishing point. They project onto lines in an image plane which will go to a fixed point, and these are known as vanishing points. And I'm sure you're all kind of familiar with these when you see them. I don't know how many you've ever done any drawing or studied at school, but it's one of the first principles of learning to draw. I think which school you thought you come from, of course. So we're applying this very same principle. Instead, what we're trying to do now is saying, given this photograph, can we find all the vanishing points that make up the main orientations that we're interested in the room? So we rest quite heavily on the assumption at the moment, and actually we've discovered some routes to break out of this. We rest heavily on the assumption of what we call a Manhattan world, as in everything is mutually 90 degrees from each other, just like in Manhattan. So, and this fits for most rooms. Like this room here is broadly Manhattan. There are a few, there's a lot of corners like that, and you get very used to spotting them when you don't know these things. So what we're really trying to do is find in this case there's going to be 3 vanishing points. This is 3 orientations. So we've got one for this wall here, all the lines disappear over there. One for this wall here, they all disappear back here. And then you've got the vertical ones here, which all go directly up and down. So from this, using just sort of like kind of quite standard geometry things, you can actually work out what the focal length of the camera was used to take the picture. So you know when you have a zoom lens on your camera, by having this information we can work out what that focal length is, and we can also work out the orientation of the camera relative to those kind of planes, so those walls. So we know, whether the camera's pointing up or down, left or right in the room. And that's all we actually need to know then in order to render virtual objects to make them appear as if they sit on one of those surfaces. So to go about solving this problem, again, going on the strict definitions of machine learning, this sits on the borders. We actually use a sort of a generative statistical model. So this means what we do is we generate hypotheses about what our correct answers could be, and then we evaluate those hypotheses against the image evidence in order to see how well they fit. So, and we actually do this using line segment analysis. So step number 1 is just quite a simple image processing step where we're saying, okay, let's try and find all the straight line segments in this image. Because really that's what we're looking in. Most indoor scenes actually consist of straight lines. So things like tables, any doors, windows, furniture always tends to be aligned with these main axes of the room. If we can find the lines corresponding to those, it gives us a really good indication of the actual layout of the room as well. And so what we've kind of shown here is this is a visualization of all the line segment intersections. So if you took that line there and that line there, that would probably be a point somewhere over here, maybe. Well, no, it'd be actually much closer, it'd be much further than here. So here what we're trying to do is we use that as a kind of a discrete search space. So rather than searching over all possible positions for our 3 vanishing points, we actually use line intersections in order to say, okay, rather than looking absolutely everywhere, let's only look in places where we have line intersections to search for. So then we have sort of a statistical technique that allows us to say, okay, we can't actually evaluate all possible line segment intersections because it would just be computationally too difficult. So every time we want to look at a hypothesis, we have to go and look at all the line segments of the image and the image data itself and see how well that hypothesis meets the image. That's the real costly step. So a lot of our effort goes into how we can prune down that hypothesis space in order to actually find a solution that's computationally feasible, gives us reliably accurate results, because if this stage goes wrong, the things a waste of time. It happened today, the CEO called me. And it also needs to be very reliable as well. From a user's perspective, you need something that works reliably both in terms of accuracy and in terms of time. So if it takes 2 seconds for one image and 10 seconds for another image, that's going to cause lots of problems from the user experience perspective. So getting that really consistent and how you then design these algorithms and models to do that is really important. Another kind of interesting problem we have here is being able to say, okay, is this right? You know, how can we say whether or not the solution we've got is correct? Because the worst thing for us to do in a way is to get it wrong and to show the user a wallpaper that's massively in the wrong position or with the wrong perspective. So if we can spot that ahead based on confidence measures, that gives us a really good benefit in terms of our user experience. It means that when things go wrong, the users don't kind of have to deal with it. We can put up a little whoopsie message. Yeah, so that's kind of problem one that we face. Put a lot of work into that, still not good enough. So the next problem earlier on, as I mentioned, so when the user clicks on the wall to add the wallpaper, as I said, we need to know two things. Once we've got the geometry and we know what perspective to draw it in with, we need to know what the extent of the wall is. So if I was to click on this wall here to add the wallpaper there, I need to be able to find this outline here, which is all the pixels that make up that wall. Now, on the face of it, this looks like a straightforward kind of thing to do. It's a sort of a paint by numbers kind of game. But you tend to find, because the way these sorts of algorithms work, computers are never really good at looking at big combinations of pixels in one go. It tends to be that you can only connect 2 or 3 pixels next to each other, and you have to do these sorts of bigger inferences across the image. So we kind of approach this problem by trying to classify which pixels are boundaries and which aren't boundaries. So essentially this image on the right hand side is the output of one of the techniques that we use, and the sort of the bluey black region is all the areas which we're saying they're not boundaries. And so by a boundary we mean a pixel that sits in between 2 objects that are of interest to a user within the context of our application, because there's no strict definition of what a boundary is either. For example, this little box here, you could say, oh right, well that's not actually an object boundary. One user may, if you were to want to fill in, you might want to fill in the whole box. Another user might just want to fill in one face. So we have to sort of be quite careful about what data we use to define what a boundary is. And the classic way of approaching this is actually you don't ask one person to tell you what boundaries are, you ask a number of people and then you find a consensus between them. So our other big problem then is basically trying to build a model that can actually tell you which pixels are boundaries and which aren't. And from that we can then go and generate an image like on the right hand side there. So the kind of really naive approach to doing this is just to use what we call local image gradients. So this is saying for every pixel, how much does it differ from its neighbours? So you imagine on a white wall, when you look at its neighbouring pixels, you'll get a low score because they're all white pixels. When you then get towards where the floor is, you'd say, oh right, but the pixel next to me is now a brown colour, so I'm probably a boundary. Well, I'll give a big score here and a big likelihood of being a boundary. But you tend to find these models don't give particularly reliable results. So again, if you look at this box, here using just a sort of a naive gradient-based approach, we get lots of contours within the box which are not interesting to us. We skip back, using our sort of more sophisticated technique, those are all suppressed. And it's also, you can't really see it on this screen, but there's lots of noise in here as well. So there's all sorts of noise with the normal gradient technique. So just image noise, in this case it might just be carpet fluff. That will all show up as well. Whereas the more sophisticated techniques will suppress that. And it's also very sensitive to scale. Some boundaries only apply over small regions, as in so going from like small objects like the little postcards on the wall. Other ones, particularly when it comes to